All right, let's dive in. Today, we're embarking on a deep dive that's been specifically requested, built from a stack of sources you've shared with us.
Mhm.
Think of this as our guided tour through the foundational ideas of physical geography.
That's right. We have material here covering, well, pretty much everything from the very beginnings of our planet Earth through the incredible forces that shape its surface, right down to the living things that make it home. It's really the story of the physical Earth.
And what a story it is. I mean, we live on this vibrant blue planet with its swirling atmosphere, massive mountains, deep oceans. It can feel a bit overwhelming, trying to understand how it all works together.
Definitely. And our mission here is to cut through some of that complexity. We're going to extract the most important insights from these sources, help you connect the dots between these different Earth systems.
Okay.
We'll explore its origin, its structure, the processes shaping it, its atmospheric and oceanic envelopes, and the life it supports.
So it's about understanding the planet as this huge interconnected system. And it gives us a great look at geography as a field. It's not just about mapping places, is it?
Oh, far from it. Geography, especially physical geography, is often called science of spatial attributes. It's this incredible integrating discipline.
Integrating.
Yeah, it pulls knowledge from geology, meteorology, oceanography, biology, even social sciences to understand the patterns and, crucially, the causal relationships across Earth's surface. It's about understanding why things are where they are.
Exactly. The where and the why. So let's start our journey at the absolute beginning.
Right at the beginning. Part 1, the Earth story, taking us from cosmic dust to the layered planet we inhabit today.
Okay. The sources mention some early ideas about how our solar system formed, like the nebular hypothesis.
Yes, that was a foundational concept, kind of suggesting planets formed from a swirling cloud of gas and dust associated with a young rotating sun. Comte and Laplace, later refined.
But the modern theory, and the one our sources really lean into, is the Big Bang.
Precisely. The idea that the universe began as an infinitesimally small, incredibly hot, and dense point.
A tiny ball.
Yeah, which then exploded violently about, 13.7 billion years ago.
And it hasn't stopped expanding since.
That's key. As it expanded, energy transformed into matter, leading to the formation of the first atoms within minutes. Edwin Hubble gave us crucial evidence for this back in the 1920s.
Right, observing galaxies moving away.
Exactly. He saw they're moving away from each other, which is evidence of this ongoing expansion of space itself.
So the space between them is growing, not the galaxies themselves getting bigger internally. The sources use that balloon analogy, which is helpful, but they do point out its limitations.
It's a good visual, yeah, but like most analogies, it has its limits. So from that cosmic event, our own solar system and Earth began to take shape.
And the early Earth, wow, the sources say it was a pretty harsh place.
Oh yeah, initially barren, rocky, incredibly hot, with just this thin sort of primal atmosphere, mostly of hydrogen and helium. Not very welcoming.
So how did it become the planet we know, with layers, air, and water?
Well, as that volatile early Earth started to cool down, the heavier materials, things like iron and nickel, they literally sank towards the center.
Because of gravity.
Gravity and density differences, yeah. Lighter materials stayed closer to the surface. This sorting process created the distinct layers we see today: core, mantle, crust.
And the atmosphere changed dramatically, too.
Hugely. That initial hydrogen and helium lost to space pretty quickly. A new atmosphere formed through degassing from the Earth's interior.
Degassing, like volcanoes.
Exactly. Volcanoes releasing water vapor, nitrogen, CO2, other gases. But the real game changer was the emergence of photosynthesis around, say, 2.5 to 3 billion years ago.
Adding oxygen.
Adding oxygen to the mix. Life literally changed the chemical makeup of our atmosphere. Initially, that life was confined to the oceans, by the way.
Wow. And the oceans themselves, they formed relatively early as well.
Very early, yeah. The water vapor released through degassing condensed as the Earth cooled enough. This rainwater then dissolved carbon dioxide from the atmosphere.
Which helped cool things down even more.
Right. And this water collected in the low-lying surface depressions, forming the oceans maybe about 4 billion years ago. So the oceans are ancient, fundamental parts of Earth.
An incredible journey just to get the basics in place. Now, let's talk about the inside of Earth. How in the world do we know about these layers deep down? I mean, we certainly haven't drilled to the core.
No, definitely not. Direct access is minimal. Mining and drilling go down a few kilometers, maybe. Volcanoes bring material up.
But we don't know exactly how deep.
Well, the source depth of magma can be uncertain, perhaps a few hundred kilometers at most, It's limited.
Okay, so here's where it gets really interesting, right? The sources make it clear that our understanding comes mostly from indirect clues.
Absolutely. We know some basic physics. Temperature, pressure, and density increase with depth. We can see that in deep mines. But the most powerful tool, the one that gives us a truly complete picture of the layers, is studying seismic waves.
From earthquakes, they're not just destructive shaking, they're like planetary sonar.
Exactly. An earthquake is essentially the shaking caused by the sudden release of built-up energy along a fault.
A break in the rock.
Break in the crustal rocks, yeah.
Mm-hmm.
Rocks on either side of a fault get locked by friction, but the immense stress building up eventually overcomes that friction and bang, they slip abruptly.
And the key points are the focus, where the energy is released deep down.
Called the hypocenter.
And the epicenter, the
Yeah.
spot on the surface directly above it, which feels the shaking first and often strongest.
Correct. And earthquakes send out different kinds of waves. First, the P waves, primary waves, they're the fastest.
Are they sound waves?
Yeah, compression waves like sound. And they can zip through solids, liquids, and gases, no problem.
Then the S waves, secondary waves, which are slower.
And this is absolutely crucial. S waves can only travel through solids. They can't pass through liquids.
Ah, so that's the key.
That's the smoking gun. By tracking how these waves travel, or more importantly, where they don't travel through the Earth, specifically the shadow zone, where S waves disappear, scientists could definitively figure out that parts of the Earth's deep interior must be liquid.
Specifically the outer core.
Exactly. That's how we know. It's a brilliant piece of deduction using basic physics.
And then there are surface waves arriving last, but often causing the most damage up here.
Right. They travel along the surface and tend to have larger amplitudes. Now, most natural earthquakes occur within the lithosphere.
Which is the crust plus the very top rigid part of the mantle, you said.
Correct. It's the rigid outer shell. It varies in thickness, maybe 10 to 200 kilometers, and significant earthquakes are generally confined to that upper 200 kilometers or so.
The sources also mention different types of quakes.
Tectonic ones are the most common, the rocks sliding along faults we just discussed. But there are also volcanic quakes near active volcanoes, and even reservoir-induced quakes, sometimes triggered by the weight of water in large reservoirs.
So seismic waves reveal the layers. Can you just quickly walk us through them again from the outside in?
Sure. Starting at the surface, the crust, the thin, brittle outermost layer we live on. Below that is the mantle.
Which includes that weaker zone, the asthenosphere.
Yeah, the asthenosphere is within the upper mantle. It's a weaker, somewhat plastic zone where magma is thought to originate. The rigid lithosphere actually sits on top of this weaker asthenosphere.
Okay.
Below the asthenosphere is the solid lower mantle. Then, at about 2,900 kilometers deep, you hit the core mantle boundary, a major transition.
And then the core itself.
Two parts. The outer core, which seismic waves tell us is liquid, and right at the center, the inner core, which is solid despite being incredibly hot due to the immense pressure.
And it's made of heavy stuff.
Very dense, heavy material, yeah. Mainly nickel and iron, sometimes called the knife layer for knife A.
Okay, that's the inside story. What about Earth's vents? It's sort of escape valves. Volcanoes.
Right. Volcanoes are essentially openings or vents where molten material, ash, and gases erupt onto the surface. We call that molten rock magma when it's underground.
And lava, once it erupts.
Exactly. Lava is what flows out.
The sources describe different types of volcanoes based on the lava and how they erupt.
Yeah, the main types mentioned are shield volcanoes. These are built by very fluid basalt lava, which flows easily like syrup.
Creating those broad, gentle slopes, like Hawaii.
Exactly like Hawaii. They form enormous, broad structures and are typically not very explosive unless water gets involved somehow. Then you have composite volcanoes, or stratovolcanoes.
Steeper sides, more explosive.
Yes, built from alternating layers of thicker, stickier lava and ash. They're steeper-sided and can be very explosive. Think Mount Fuji or Mount St. Helens. They can sometimes collapse violently, forming calderas.
And then there are these massive flood basalt provinces.
These aren't really cone-shaped mountains at all. They're enormous outpourings of highly fluid lava that flood vast areas, covering thousands of square kilometers, forming thick, layered plateaus.
Like the Deccan Traps in India.
That's the classic example given in the sources. A huge, large, igneous province, formed relatively quickly in geological terms.
We also learned about volcanic activity happening underground, where the magma cools before it even reaches the surface.
Yes, these form what we call intrusive volcanic landforms. The key takeaway here isn't necessarily memorizing every single type.
Like batholiths, sills, dikes.
Right. The main point is that magma doesn't always erupt onto the surface. It can push its way into existing rock layers underground and then cool and solidify there.
Forming different shapes depending on how it's squeezed in.
Exactly. Batholiths are huge, irregular masses, often the solidified remnants of magma chambers deep down. Sills are like horizontal sheets injected between layers, and dikes are more vertical sheets that cut across layers. Seeing these exposed later by erosion tells us a lot about the old volcanic plumbing system.
Fascinating stuff. Okay, so that covers the planet's origin and its inner workings. Now let's just focus to the surface itself, which is anything but static.
Absolutely. Part 2. The dynamic surface continents, oceans, and the forces shaping them. This is where we get into continental drift and the really big picture of plate tectonics.
And the very first observation that sparked this whole idea was kind of incredibly just looking at maps, right? That jigsaw fit of the continents.
Yeah, especially across the Atlantic. People noticed it centuries ago. Ortelius, Pellegrini are mentioned.
But it was Alfred Wegener who really ran with it.
Yes, in the early 20th century. He pulled together a comprehensive theory, proposing that the continents weren't always separate, but were once joined in a giant supercontinent he called Pangaea.
Which then broke apart.
Into Laurasia in the north and Gondwanaland in the south, he suggested, and then eventually into the continents we see today. And crucially, Wegener didn't just rely on the coastal fit. He marshaled multiple lines of evidence.
Like what kind of evidence?
Well, he found matching rock types and geological structures, and rocks of the same age, on continents now separated by oceans. That suggested they were once joined.
Okay.
He found evidence of ancient glaciation-specific deposits called tulites in places that are tropical or subtropical today, like India, Africa, South America. But if you put the continents back together in Pangaea, these glacial deposits line up neatly near the South Pole.
Makes sense. And fossils, too.
Yes, the distribution of fossils was key. Finding identical fossils of land-dwelling plants and animals, like the small reptile Mesosaurus, on continents now separated by vast oceans like South America and Africa, strongly suggested these land masses were once connected. You also had things like lemurs suggesting connections between India, Madagascar, and Africa.
That sounds like really powerful evidence. But his theory wasn't widely accepted at first, was it? Why not?
The main sticking point, the big weakness, was the mechanism. He couldn't propose a convincing physical force strong enough to move entire continents across the globe.
What did he suggest?
He talked about things like a pole-fleeing force related to Earth's rotation, or tidal forces from the sun and moon. But physicists calculated these forces were nowhere near strong enough to do the job. So the idea languished for decades.
Okay, so let's unpack this. How did we get from Wegener's rejected idea to the accepted theory of plate tectonics? What were the key discoveries that bridged that gap?
The breakthroughs really happened after Wegener, mostly from the 1940s to the 1960s, and largely thanks to exploring the ocean floor, which was mostly unknown in Wegener's time.
Using new technologies like sonar.
Exactly. Mapping the seabed revealed incredible features, especially the vast mid-oceanic ridges, basically the longest mountain chain on Earth, running through all the major oceans, like the seam on a baseball. And they found intense volcanic activity right along the central rift valley of these ridges.
Suggesting new rock was forming there.
Precisely. And then ocean drilling programs brought up rock samples. They found that the oceanic crust is surprisingly young, nowhere older than about 200 million years.
Compared to continents, which can be billions of years old.
Right. A huge difference. Also, plotting earthquake locations revealed a distinct pattern. Shallow earthquakes were concentrated right along the mid-ocean ridges, but deep earthquakes occurred predominantly near deep ocean trenches.
All these pieces started fitting together. This led Harry Hess to propose seafloor spreading.
Yes, in 1961, Hess put it together. New oceanic crust erupts at the mid-ocean ridges, pushing the older crust sideways like a conveyor belt. The ocean floor literally spreads apart, and he proposed that this older ocean floor is then consumed or recycled back into the mantle at the deep ocean trenches.
A complete cycle. And this all culminated in the plate tectonics theory just a few years later.
Yeah, building on Hess's idea and adding more evidence like paleomagnetism, the record of Earth's magnetic field reversals locked in rocks. Mackenzie, Parker, and Morgan developed the comprehensive plate tectonics model around 1967.
So what's the core idea of plate tectonics?
It unifies continental drift and seafloor spreading. It says the Earth's rigid outer layer, the lithosphere, that crust plus upper mantle bit, isn't one solid shell. It's broken into several large and smaller pieces called tectonic plates.
How many major plates?
The sources list 7 major ones, like the Pacific, North American, Eurasian plates, plus several minor ones. And these plates are constantly moving, floating on the weaker asthenosphere beneath.
And their interactions happen at the boundaries.
Exactly. 3 main types. Divergent boundaries, where plates pull apart like at mid-ocean ridges. Convergent boundaries, where plates collide. One might slide under the other, subduction, or they might crumple up. And transform boundaries, where plates slide past each other horizontally, like the San Andreas Fault.
And one of the most dramatic examples of this in action is the story of India crashing into Asia.
Oh, it's a fantastic case study. The sources describe India originally being an island way down south near Australia and Antarctica about 225 million years ago. It was separated from Asia by a vast ocean called the Tethys Sea.
Then it started moving north.
Yeah. After Pangaea broke up, India started a remarkably rapid northward journey around 200 million years ago.
And that collision, well, it had a rather significant impact on the landscape, didn't it?
Understatement. The impact with Asia began around 40 to 50 million years ago. This colossal slow-motion collision crumpled the crust like hitting a brick wall, pushing up the mighty Himalayas. And they're still slowly rising today as the Indian plate continues to push northwards.
Incredible. The sources also mentioned the Deccan Traps flood basalts happening during this journey north.
Yeah, around 60 million years ago, while India was still on its way north, this massive volcanic outpouring occurred, possibly related to passing over a mantle hotspot. It just adds another layer to India's dramatic geological story.
Amazing to visualize that continental journey. Okay, so while these huge internal forces, plate tectonics, are building mountains and rearranging continents, the surface is simultaneously being sculpted and worn down by external forces.
That brings us perfectly to the interplay of endogenic and exogenic processes. Endogenic forces originate from within the Earth. Think volcanism, earthquakes, tectonic uplift. They build relief, create mountains, plateaus.
Building up?
Right. Exogenic forces originate from outside, driven mainly by energy from the sun, atmosphere, and the pull of gravity. They work to wear down that relief.
Wearing down.
Exactly. Weathering, erosion, mass wasting. These are the key exogenic processes. The Earth's surface is this constant dynamic battleground between these building up and wearing down forces.
And gravity plays a huge role in the exogenic side, especially on slopes.
Absolutely. The sources talk about stress force per unit area, causing rocks to deform or break. Shear stress, where forces act parallel to a surface, is particularly effective at breaking things down. These stresses, whether from freezing water expanding in cracks, chemical reactions weakening rock, or simply gravity pulling downwards on steep slopes, are fundamental drivers of how the surface changes shape.
Let's start with weathering, breaking rocks down.
Weathering is the breakdown of rocks, either physically, like frost shattering, or chemically, like dissolution or rusting, while they're still in place. It's the direct action of atmospheric elements, temperature changes, water, gases, and climate over time.
Does it include biological activity too? Plant roots, microbes?
Yes, biological weathering is a key part mentioned. Plant roots wedging rocks apart, organisms producing acids that dissolve minerals, even human activity like quarrying or plowing that disturbs soil and rock. Weathering essentially creates the raw material, the broken fragments, the altered minerals that other processes can then pick up and move.
So weathering breaks it down, but crucially, it doesn't move it very far.
Correct. Weathering prepares the material, it aids erosion by providing loose stuff, but erosion itself is the process of moving that material away. Now there's a process closely linked to weathering called mass movement or mass wasting.
Okay, what's that?
That's the downslope movement of rock, soil, and debris, purely driven by gravity alone. Think landslides, rockfalls, soil creep.
So erosion agents like rivers or wind aren't the main drivers there. It's just gravity pulling loose stuff down.
Exactly. Gravity is the driving force. Mass movement happens when gravity's pull overcomes the strength of the slope material. Its internal friction or cohesion. It's most active on slopes that have already been weathered.
What makes it more likely to happen?
Factors that favor it include steep slopes, obviously, weak or loose materials, lots of water saturating the ground, which adds weight and reduces friction, and removing vegetation cover because roots help hold slopes together.
And what can actually trigger a specific event, like a landslide?
Several things. Removing support from the base of a slope, like undercutting by a river or road construction. Overloading the top of the slope, maybe with buildings or just really heavy rainfall. Earthquakes shaking the ground can trigger widespread failures. Sudden saturation from storms. The source is meant in different types based on speed and material, like heave, very slow, almost imperceptible creep. Flow, faster movement like mud flows or debris flows where material behaves a bit like a fluid, and slides, where a more coherent block moves downslope like slumps or rock slides, rock falls.
Okay, so weathering breaks it, mass movement pulls it down the slope by gravity, and erosion is the one that transports it away using an agent.
Precisely. Erosion involves the acquisition, the picking up, and the transportation of weathered material by mobile agents like running water, wind, glaciers, or ocean waves. It's the active wearing down and lowering of the land surface. Deposition is the flip side. When the transporting agent loses energy, drops the material it was carrying. These processes, erosion and deposition, are fundamentally controlled by kinetic energy, the energy of motion of the water, wind, or ice.
Let's look at the main agents, starting with running water rivers. Seems like a big one.
Arguably the most dominant geomorphic agent globally, yeah.
Huh.
Active in humid climates, obviously, but also very important in arid climates, where infrequent but powerful flash floods can do a lot of work. Water starts sculpting the land initially, perhaps as sheet erosion, then it concentrates into tiny channels called rills, which join to form gullies, and eventually these carve out valleys.
And valleys change shape over time as the river system evolves.
They do. The sources describe a kind of life cycle. In the young stage, rivers have steep gradients, lots of energy focused on cutting downwards, forming characteristic narrow V-shaped valleys, often with rapids and waterfalls.
Then they mature.
In the mature stage, the gradient lessens, the river starts cutting sideways more than down, widening the valley floor. Meanders, those winding curves start to develop. The river becomes more graded, meaning its slope is adjusted to carry its typical load of sediment.
In the old stage.
In the old stage, the river flows across a very wide, flat floodplain that it built itself. The gradient is very low, meanders become extremely pronounced, and features like oxbow lakes, cut-off meanders, are common. The ultimate endpoint of river erosion, theoretically, is a nearly flat plain called a peneplain, though perfect examples are rare.
And rivers create very distinct landforms through both carving, erosion, and dumping sediment deposition.
Absolutely. Erosional landforms include the valleys themselves, of course. Gorges are very deep, narrow valleys with steep, almost vertical sides, often carved in resistant rock. Canyons are also deep and steep-sided, but often wider at the top than the bottom, sometimes with step-like sides, typically formed in horizontally layered sedimentary rocks like the Grand Canyon.
And depositional features, lots of those.
Loads. Where a river flows out of mountains onto a flatter plain, it drops sediment in a cone or fan shape, an alluvial fan. Where a river enters a body of standing water like a lake or the sea, it deposits its load, building out land in a typically triangular or fan shape, a delta.
Like the Nile or Mississippi Delta.
Exactly. The floodplain itself is a major depositional feature, built up layer by sediment dropped during floods. Along the river banks on the floodplain, you often get slightly raised ridges called natural levees, formed by coarser sediment dropping out first as floodwaters spill over. Inside the bends of meanders, where the water flows slower, sediment accumulates to form pregpars. And the meanders themselves, those looping curves, can eventually be cut off during floods, leaving behind crescent-shaped oxbow lakes on the floodplain.
Okay, that's surface water. What about water that seeps underground?
Groundwater.
Groundwater's geomorphic work is really significant, mainly in specific rock types, particularly those rich in calcium carbonate, like limestone and dolomite. Here, it creates a unique landscape called karst topography.
Through dissolving the rock.
Primarily through solution, yes. Rainwater absorbs CO2 from the air and soil, becoming slightly acidic. This weak carbonic acid is very effective at dissolving limestone over long periods. In these areas, groundwater flow underground can actually be more dominant than surface river flow. And what kind of features do we see in karst landscapes?
Very distinctive stuff. Sinkholes, also called dolines, are common depressions formed either by dissolution at the surface or by the collapse of underground cavities. These can merge to form larger compound depressions called valley sinks or euvalas.
And on the exposed rock surfaces,
You get intricate patterns of grooves, channels, and ridges called lappies or cairn. Sometimes large areas of exposed grooved limestone are called limestone pavements. And perhaps most famously, karst areas are known for extensive cave systems and underground tunnels, formed as groundwater preferentially dissolves rock along joints, faults, and bedding planes.
move into much colder environments now: ice, glaciers, sculptors.
Glaciers, immense masses of moving ice, are incredibly powerful agents of landscape change. They erode bedrock very effectively through two main processes. Abrasion, which is like sandpapering, where rocks embedded in the ice scrape and grind the bedrock below, and plucking or quarrying, where meltwater freezes and cracks, expands, and levers out chunks of rock that then get frozen into the glacier's base and carried away. Their sheer weight and grinding power can dramatically transform mountains over geological time.
What are some of the key landforms carved by glaciers? Erosional features.
In mountainous areas, you get classic features. Cirques, or corries, are deep, armchair-shaped basins eroded into the mountainside at the head of a glacial valley. After the ice melts, these often hold small, round lakes called tarns.
And the valleys themselves look different.
Very different from river valleys. Glacial valleys, or glacial troughs, are characteristically U-shaped. They have broad, flat floors and steep, almost straight sides because the ice erodes both the bottom and the sides effectively. You often find smaller tributary valleys left hanging high above the main valley floor, hanging valleys because the main glacier eroded deeper. Spurs of land that once projected into the valley get chopped off, creating truncated spurs. And if these U-shaped valleys are near the coast and get flooded by the sea after the ice melts, they become deep inlets called fjords.
And just like rivers, glaciers also dump material when they melt, depositional features.
Yes, the material transported and deposited by glaciers is generally called glacial drift. The unsorted, jumbled mixture of clay, sand, gravel, and boulders dropped directly by melting ice is called till. Meltwater streams flowing from the glacier carry sediment too, but they sort it by size, creating stratified, layered deposits called outwash or glaciofluvial deposits.
And they form ridges and mounds.
They do. Moraines are ridges made of till. Terminal moraines mark the furthest advance of the glacier. Lateral moraines form along the sides of the glacier. Ground moraine is still plastered beneath the ice. Medial moraines form down the middle where two glaciers merge. Eskers are long, winding ridges made of sand and gravel, thought to be deposited by meltwater streams flowing in tunnels within or underneath the ice.
And those distinctive, smooth, oval hills the sources mentioned.
Drumlins. These are streamlined, elongate hills made primarily of till. They're shaped by the moving ice flowing over them, so they're aligned parallel to the direction of ice flow. They typically have a blunt, steeper end, the Stoss end, facing the direction the ice came from, and a longer, gentler, tapering tail pointing in the direction the ice was moving towards. They're like giant fingerprints left by the ice sheet, telling us which way it flowed.
Fascinating how ice leaves such a clear signature on the land. Okay, finally, let's look at the edges, coastlines shaped by waves, and dry areas shaped by wind.
Coastal landforms are incredibly dynamic environments. They're constantly being shaped by the energy of waves and currents, but also influenced by the underlying geology, the shape of the land and seafloor, and whether the sea level is rising or falling relative to the land, is the coastline advancing or retreating. And major events like storms or tsunamis can cause very rapid, dramatic changes.
What are the main features carved by the sea, erosional ones?
Pretty straightforward. Where the land meets the sea with some elevation, waves attacking the base can carve out cliffs. As cliffs retreat, they often leave behind a gently sloping surface at their base called a wave-cut platform or terrace, which might only be visible at low tide.
And where the sea deposits material.
Depositional features are more varied and often quite temporary, shifting with storms and seasons. Beaches are the most obvious accumulations of sand or shingle. Behind the beach, wind can often blow sand inland to form coastal dunes. Offshore, waves and currents can build up submerged ridges of sand called bars. If these bars become exposed above sea level, they're called barrier bars or barrier islands. A spit is a type of barrier bar or beach ridge that's attached to the mainland at one end and extends out into open water, often across a bay entrance. If a bay gets largely closed off from the sea by bars or spits, the water body behind it becomes a lagoon, which might eventually fill in with sediment to become a coastal plain.
Okay. And shifting to deserts, wind is the key player there.
Wind is a primary agent in shaping desert landscapes, yes. Although the sources wisely remind us that infrequent but powerful flash floods, sheet floods, caused by sudden downpours, can also be very significant erosional forces in deserts. But wind is constantly at work.
How does wind erode?
Mainly through two processes. Deflation, which is simply the lifting and removal of loose, fine particles like dust and sand. Over time, this can lower the desert surface or scoop out depressions called deflation hollows or blowouts. The second process is abrasion, which is like natural sandblasting. Wind picks up sand grains and hurls them against exposed rock surfaces, scouring, scraping, and polishing them. Impact is also mentioned, just the sheer force of the wind and the particles it carries.
And this creates some unique-looking features.
Definitely. Deflation can create large hollows, sometimes reaching the water table to form oases. Abrasion is particularly effective near the ground where the wind carries the most sand. It can undercut rock formations, sometimes leaving behind strangely shaped remnants like mushroom rocks, table rocks, or pedestal rocks, where a harder cap rock protects softer rock underneath, which gets worn away faster at the base.
And where does all that wind-blown sand end up deposition?
Wind is actually very good at sorting sediments by size. It can carry fine dust long distances, but sand grains typically bounce and roll along the surface and accumulate into sand dunes. For dunes to form, you generally need a supply of sand, wind strong enough to move it, and some kind of obstacle, even a small shrub or rock, to cause the wind to slow down and drop the sand.
And the shape of the dune tells you about the wind conditions.
Exactly. Dune forms are a direct response to factors like wind strength and direction. It's a consistent or variable. Sand supply, abundant or limited, and the presence of any vegetation. The sources mention several types. Barkhans are beautiful crescent-shaped dunes with the horns pointing downwind, typically forming where wind is consistent and sand supply is limited. Parabolic dunes are also crescent-shaped but reversed, with the horns pointing upwind, often anchored by vegetation, common in coastal areas. Ceph dunes are a type of long, linear dune. Longitudinal dunes are long ridges running parallel to the prevailing wind direction. Transverse dunes are ridges oriented perpendicular to the wind, forming where sand is abundant. The shape is like a direct readout of the desert environment.
Wow. That's a really comprehensive look at how Earth's surface is constantly being shaped, built up by those internal forces, and then relentlessly worn down and reshaped by these external agents: water, ice, waves, and wind. Amazing interplay.
It really highlights the incredible energy involved and the continuous change happening all around us on the planet's surface, even if much of it is slow on human timescales. Now, shall we zoom out again and look at those global envelopes of air and water, the atmosphere and oceans?
Perfect. Part 3 dives into these absolutely vital systems. Let's start with the atmosphere, the air we breathe.
The atmosphere. Okay. Composition-wise, the sources note it's mainly nitrogen and oxygen with smaller amounts of other gases. Structurally, it's divided into layers based on how temperature changes with altitude.
Troposphere, stratosphere.
Right. Troposphere is the lowest layer, closest to the surface. That's where almost all our weather happens. It contains most of the atmosphere's mass, and it's obviously most important for us humans and other life. Then comes the stratosphere, which contains the ozone layer, mesosphere, thermosphere, and finally the exosphere, which gradually merges with outer space.
And those tiny particles floating in the air dust, salt, they actually matter.
Oh, crucially, these aerosols act as hygroscopic nuclei, basically. Tiny surfaces that water vapor can condense onto to form cloud droplets or ice crystals. Without them, cloud formation would be much more difficult. Geographers tend to focus most on the troposphere and lower stratosphere when studying weather and climate.
Understanding the atmosphere fundamentally involves understanding heat and temperature, which mostly comes from the sun, right?
Exactly. The sources distinguish between heat, the total energy of molecular motion, and temperature, which is our measurement of the degree of hotness or coldness. The distribution of air temperature across the Earth's surface is controlled by several key factors.
So like latitude.
Latitude is number one. Solar radiation insolation is most intense near the equator and decreases towards the poles, so generally it gets colder as you move away from the equator. Altitude is another temperature typically decreases as you go higher up in the troposphere.
The lapse rate.
All right. And the third big one is distance from the sea. Oceans heat up and cool down much more slowly than land masses. So coastal areas tend to have more moderate temperatures, less variation between summer and winter, day and night, compared to continental interiors, which experience greater extremes. That's the marine versus continental influence.
And differences in temperature across the globe lead to differences in air pressure, which is what drives wind and creates weather patterns.
Precisely. Atmospheric pressure is simply the weight of the column of air above a given point on the surface. It's usually measured in millibars, MB, with the average sea level pressure being around 513.2 millimeters. Pressure decreases rapidly as you go up in altitude. But it's the horizontal differences in pressure at the surface that cause wind air naturally wants to flow from areas of high pressure to areas of low pressure.
But gravity stops the air just shooting straight up.
Well, the vertical pressure gradient is actually much, much stronger than the horizontal ones that drive surface winds. But it's almost perfectly balanced by the downward pull of gravity, which is why the atmosphere doesn't just fly off into space, and we don't experience constant, huge updrafts.
Okay. Globally, these pressure differences create large-scale patterns, the pressure belts.
Yes, Due to uneven heating and Earth's rotation, we get semi-permanent zones of high and low pressure. The equatorial low, or ITCZ, the subtropical highs around 30 degrees north and south, the subpolar lows around 60 degrees NS, and the polar highs over the poles. These belts aren't fixed, though. They shift north and south seasonally, following the overhead sun.
But wind isn't just a simple flow from high to low pressure. Other forces complicate things.
All right, three main forces affect wind near the surface. First is the pressure gradient force, PGF. That's the primary driver, pushing air from high to low pressure. The steeper the pressure gradient, the closer the isobars on a weather map, the stronger the wind. Second is friction, which acts to slow the wind down, especially near the ground due to obstacles like trees, buildings, hills. Its effect decreases with height.
And the third one, the Coriolis force.
The Coriolis force, yes. This is an apparent force caused by the Earth's rotation. It deflects moving objects like air parcels or ocean currents to the right in the northern hemisphere and to the left in the southern hemisphere. Its strength depends on latitude, is zero at the equator and maximum at the poles, and also on the speed of the moving object. It doesn't change wind speed, only direction.
And these forces interact to create the actual wind patterns we observe. High up, away from friction, it's simpler.
Yes, in the upper atmosphere, above the friction layer, the wind tends to blow parallel to the isobars. This is called the geostrophic wind, where the pressure gradient force and the Coriolis force are in balance. Near the surface, friction messes things up, slowing the wind and causing it to blow across the isobars towards low pressure.
So, thinking about weather, air rising is key for clouds and rain.
Absolutely. Air generally converges and rises over low-pressure areas, cyclones, leading to cloud formation and often precipitation. Air subsides, sinks, and diverges over high-pressure areas, anticyclones, which usually leads to clear skies and fair weather. So any process that forces air to rise is crucial for weather. Convergence of surface winds, convection, rising thermals of warm air, orographic uplift, air forced up over mountains, or lifting along weather fronts.
This all ties into the general circulation of the atmosphere.
Yes, the large-scale average pattern of winds across the planet. It's driven by the fundamental imbalance of solar heating between the equator and poles, modified by the pressure belts, Earth's rotation, Coriolis, and the distribution of continents and oceans.
It involves those big circulation cells.
Right. The sources explain the three-cell model for each hemisphere. The Hadley cell in the tropics. Air rises at the equator, flows poleward aloft, sinks in the subtropics, flows back towards the equator near the surface as the trade winds. The Ferrel cell in the mid-latitudes, more complex, driven partly by the Hadley and polar cells associated with westerly winds, and the polar cell at high latitudes, air sinks at the poles, flows equatorward, rises around 60 degrees. This whole system acts as a giant heat engine, transporting excess heat energy from the tropics towards the poles, trying to balance the planet's energy budget.
And the atmosphere doesn't operate in isolation, it strongly interacts with the oceans.
Hugely interconnected. Atmospheric circulation, especially the prevailing winds, is a major driver of large-scale surface ocean currents. In turn, the oceans store vast amounts of heat and release energy and water vapor back into the atmosphere, which fuels weather systems and influences climate. It's a coupled system.
The sources mention ENSO, El Nino.
Yes. ENSO, El Niño Southern Oscillation, is highlighted as a prime example of this powerful ocean-atmosphere interaction in the tropical Pacific that has major ripple effects on weather patterns across the globe. We also have seasonal wind systems driven by land-ocean temperature contrasts, like the monsoons, and smaller-scale local winds driven by daily heating differences, like sea breezes.
What happens when large bodies of air with different characteristics meet? That's where fronts come in.
Exactly. When different air masses, large bodies of air with relatively uniform temperature and humidity collide, they don't mix easily. The boundary zone between them is called a front. There are different types. Cold fronts, where cold air advances, forcing warm air up rapidly. Warm fronts, where warm air overrides colder air more gently. Stationary fronts, where the boundary isn't moving much. And occluded fronts, more complex, where a cold front catches up to a warm front.
And fronts are associated with weather.
Very much so. They are zones of strong temperature and pressure gradients, and they force air to rise, often leading to widespread cloud formation and precipitation. They're key features of mid-latitude weather systems.
And these fronts are often part of larger storm systems, cyclones?
Yes, particularly the extratropical cyclones, also called mid-latitude cyclones or depressions. These are large, low-pressure systems that typically form along the polar front in the mid and high latitudes. They have characteristic warm and cold fronts extending from their centers, cover vast areas, hundreds or thousands of kilometers across, can originate over land or sea, and generally move from west to east with the prevailing winds.
How do they form?
The sources describe a model where a wave or disturbance develops on the polar front, warm air starts moving poleward, cold air moves equatorward, and the Coriolis force induces rotation, anti-clockwise in the northern hemisphere. They develop distinct warm and cold sectors. Precipitation occurs as warm air glides up over the cold air ahead of the warm front, often steady rain or snow. And as the cold front wedges forcefully under the warm air, often heavier showers, thunderstorms, they eventually dissipate when the cold front catches up to and lifts the warm front completely off the ground, forming an occluded front. While they bring widespread unsettled weather, their winds are typically less destructive than tropical cyclones.
Okay, so tropical cyclones are the really intense ones. Hurricanes, typhoons.
Exactly. These are violent, rotating storms that form exclusively over warm tropical oceans. The sea surface temperature needs to be above about 27 degrees C, 80 degrees AFR. They also need the Coriolis force to initiate rotation, which is why they don't form right at the equator, within about 5 degrees latitude. They draw energy from the heat and moisture of the warm ocean water and can become incredibly powerful, bringing extremely destructive winds, torrential rainfall, and dangerous storm surges when they make landfall on coastal areas.
Different names in different places?
Yes, same phenomenon, different regional names. Cyclones in the Indian Ocean and South Pacific, hurricanes in the Atlantic and Northeast Pacific, typhoons in the Northwest Pacific near Asia, and willy willies off Australia.
What conditions do they need to form?
Besides the warm sea surface and Coriolis force, they generally need pre-existing weak low-pressure areas or disturbances, low vertical wind shear, meaning wind speed and direction don't change much with height, which would tear the storm apart, and high humidity through a deep layer of the troposphere. Oh, and upper-level divergence air flowing away from the storm top helps sustain the inflow at the surface.
And their energy source is that warm water.
Specifically, the tremendous amount of latent heat released when water vapor, evaporated from the warm ocean, condenses into cloud droplets and raindrops within the storm's towering cumulonimbus clouds. It's like a massive heat engine fueled by the ocean. They weaken and dissipate rapidly when they move over land because that vital moisture and heat source is cut off.
They have a distinct structure, right, the eye.
Very distinct. At the center is the eye, a region of calm or light winds, clear or partly cloudy skies, and sinking air. It can be tens of kilometers across. Surrounding the eye is the eye wall, a ring of intense thunderstorms where the strongest winds and heaviest rainfall occur. Wind speeds can exceed 250 kilometers s, 155 miles per hour, in extreme cases. Extending outwards from the eye wall are spiral rain bands, also containing heavy rain and strong winds. Landfall is defined as when the storm center, the eye, crosses the coast. They often tend to recurve, turning poleward and eastward after reaching about 20 degrees latitude.
The sources also mention other types of severe local storms.
Yeah, briefly. Thunderstorms, which are much smaller scale than cyclones but can still be intense, they're caused by strong convection, rapidly rising warm, moist air, forming deep cumulonimbus clouds. They produce lightning and thunder, heavy rain, sometimes hail, and strong gusty winds. Tornadoes are even smaller, but incredibly violent, rotating columns of air extending down from the base of severe thunderstorms. They have extremely low pressure at their core and can cause catastrophic damage along narrow paths. They are most common in mid-latitude regions like the U.S. Great Plains. A waterspout is simply a tornado occurring over water. All these severe storms are basically the atmosphere's way of rapidly adjusting imbalances in energy, temperature, and moisture on various scales.
Okay, that's a whirlwind tour of the atmosphere. Now moving from the air to the other essential fluid envelope that defines our planet, the oceans.
Water. Absolute fundamental. Earth is a blue planet for a very good reason. About 71% of the surface is covered by oceans. And liquid water is surprisingly rare elsewhere in the solar system, as far as we know. It's essential for all life.
And it's constantly moving around in the hydrological cycle.
Yes, the hydrological cycle describes the continuous circulation and exchange of water in all its states. Liquid, solid, ice, gas, water vapor, between the oceans, the atmosphere, the land surface and subsurface, and living organisms. It's a global system driven by solar energy.
And most of Earth's water is in the oceans.
Overwhelmingly so. About 97% of all water is salty ocean water. The remaining 3% is fresh water, but most of that is locked up in glaciers and ice caps, or stored as groundwater deep underground. Only a tiny fraction is easily accessible surface water in lakes and rivers. The cycle involves processes like evaporation, liquid to gas, from oceans and land, transpiration, water released from plants, condensation, gas to liquid solid, to form clouds, precipitation, rain, snow, hail, falling back to the surface, and then runoff over the land or infiltration into the ground, eventually returning to the oceans.
And just like the land, the ocean floor isn't just a flat, boring basin. It has incredibly varied topography.
Very much so. It features mountains, plains, canyons, trenches formed by the same large-scale tectonic, volcanic, and depositional processes that shape the continents.
What are the main divisions or features?
Starting from the continents, you have the continental shelf, which is the shallow, gently sloping, submerged edge of the continent. It can vary greatly in width and ends at the shelf break, where the slope suddenly steepens. Beyond that is the steeper continental slope, which leads down to the deep ocean floor.
Which is mostly flat.
Large parts of it form the deep sea plain, or abyssal plain, which are among the flattest regions on Earth, covered by fine sediment. But these plains are interrupted by major features. The oceanic deeps, or trenches, are the deepest parts of the ocean, long, narrow, incredibly deep depressions, like the Mariana Trench. They are steep-sided, often associated with active volcanoes and frequent earthquakes, and they mark convergent plate boundaries where oceanic crust is subducting back into the mantle. Very significant for understanding plate movements.
Underwater mountains.
Yes. You have the mid-oceanic ranges we discussed earlier, the vast underwater mountain ranges where new seafloor is created. There are also isolated underwater volcanic mountains called seamounts. Some of these might have once reached the surface, got eroded flat on top, and then subsided back below sea level. These are called guyos or table mounts. And cutting into the continental shelves and slopes, you sometimes find deep V-shaped valleys called submarine canyons, often located near the mouths of major rivers. Let's talk about the properties of the ocean water itself, like temperature. Ocean water temperature is obviously a key property. Surface temperature generally decreases from the equator towards the poles, mirroring the pattern of incoming solar radiation. Average surface temperatures might be around 27 degrees C near the equator, falling steadily towards freezing point near the poles.
What else affects surface temperature distribution?
Several factors mentioned. Latitude is primary. The unequal distribution of land and water, the northern hemisphere has more land, and its oceans tend to be slightly warmer on average than the southern hemispheres. Prevailing winds play a role. They can push warm surface water, causing it to pile up in some areas, or drive surface water away, allowing colder water from below to rise up. This is called upwelling. And crucially, ocean currents act like giant conveyor belts, transporting warm water poleward and cold water equatorward, significantly modifying regional temperatures.
Like the Gulf Stream warming Northwest Europe?
Exactly. The Gulf Stream carrying warm water across the North Atlantic makes Western Europe much milder than it would otherwise be at that latitude. Conversely, cold currents like the Labrador Current flowing south along eastern North America bring colder conditions.
And temperature changes with depth, too, not just latitude.
Yes, definitely. In most parts of the ocean, there's a distinct vertical temperature structure. Typically, there's a relatively warm surface layer, mixed by wind and waves, maybe 5,200 meters deep. Below that is the thermocline, a zone where temperature decreases rapidly with increasing depth. And beneath the thermocline lies the deep ocean, which is uniformly very cold, typically just a few degrees above freezing, even at the equator. In high latitudes, this layering might be weak or absent, with cold water extending all the way from the surface down.
Salinity is the other key property, how salty the water is.
Right. Salinity is defined as the total amount of dissolved salts in seawater, usually expressed as grams of salt per 1,000 grams, 1 kilogram of seawater, or parts per 1,000 ppb. Average ocean salinity is around 35 PAT, but it varies geographically depending on evaporation rates, precipitation, river runoff, and ice formation melting.
Why is salinity important?
It's crucial because, along with temperature, it determines the density of seawater. Saltier water is denser than less salty water at the same temperature, and colder water is denser than warmer water. These density differences are the primary driver for the deep ocean circulation. Denser water tends to sink below less dense water, creating vertical movements and driving slow, deep currents across ocean basins. This creates stratification, layers of water with different densities.
And ocean water is definitely not static. It's constantly moving in various ways.
Extremely dynamic, influenced by temperature, salinity, density differences, the gravitational pull of the sun and moon, and especially the friction from winds blowing over the surface. We can broadly categorize ocean movements into horizontal motions like currents and waves, and vertical motions like tides and upwelling sinking processes.
Let's start with waves. They're not water moving across the ocean, right? It's energy.
That's the key concept the sources emphasize. While the waveform travels across the ocean's surface, the water particles themselves mostly just move in small circles, ending up almost back where they started. It's the energy transferred from the wind to the water that propagates across the surface.
What determines wave size?
The size and shape of wind-generated waves depend mainly on three factors: the wind strength, the duration, how long the wind blows consistently, and the fetch, the distance of open water over which the wind blows. Stronger, longer-lasting winds blowing over large area create the biggest waves. Steep, choppy waves are usually young waves generated by local winds, while long, low swells are often waves that have traveled far from where they were generated. Waves are essentially caused by the wind pushing on the water surface and gravity pulling the wave crest back down.
Okay, then tides are the regular, predictable rise and fall of sea level.
Yes, typically occurring once or twice daily. They are primarily caused by the gravitational attraction of the moon and, to a lesser extent, the sun acting on Earth's oceans. It's important to distinguish tides from storm surges, which are temporary rises in sea level caused by meteorological factors like strong winds and low pressure.
How does gravity cause tides? It pulls the water up.
It's a bit more complex than just pulling the water up. The tide-generating force is actually the difference between the gravitational pull of the moon, or sun, on different parts of the Earth, and the centrifugal force resulting from the Earth-Moon, or Earth-Sun, system orbiting around their common center of mass. This difference creates two tidal bulges on opposite sides of the Earth. One on the side facing the moon, where gravity is strongest, and one on the side directly opposite, where centrifugal force dominates over the weaker gravity. The horizontal forces pulling water towards these bulges are actually more important in creating the tidal flows than the vertical listing force.
The sources mention the huge tides in the Bay of Fundy in Canada.
Yes, that's a classic example of where the shape and resonance of a bay can dramatically amplify the tidal range, leading to differences between high and low tide of 15-16 meters, over 50 feet. The water level can rise incredibly fast there.
And tides vary in their daily pattern.
They do. The sources describe three main types based on frequency. Semi-diurnal tides, where there are two high tides and two low tides each day, of roughly equal height, common along the Atlantic coast of North America. Diurnal tides, with only one high tide and one low tide each day, common in the Gulf of Mexico. And mixed tides, which also have two highs and two lows daily, but with significant differences in height between successive highs or lows, common along the Pacific coast of North America.
And the height of the tides also changes throughout the month related to the moon phases.
Exactly. This is due to the alignment of the sun, moon, and earth. Spring tides occur when the sun, moon, and earth are aligned in a straight line at new moon and full moon. The gravitational poles of the sun and moon reinforce each other, leading to higher high tides and lower low tides, the greatest tidal range.
And neap tides.
Neap tides occur when the sun and moon are at right angles to each other relative to the earth, at first and third quarter moons. Their gravitational forces partially cancel each other out, resulting in lower high tides and higher low tides, the smallest tidal range. These spring neap cycles happen roughly twice a month. The actual tidal range is also affected by whether the moon is at perigee, closest to Earth, or apogee, farthest, and whether the Earth is at perihelion, closest to Sun, or aphelion, farthest.
Tides seem pretty important, even though they happen slowly.
Very important, especially for navigation in coastal areas, harbors, and estuaries, where water depth changes significantly. Understanding and predicting tides is crucial for shipping. Tidal currents can also be strong in some areas, and are increasingly being looked at for generating energy.
Okay, finally, the big movements. Ocean currents, like rivers in the sea.
That's a good analogy. Ocean currents are the continuous, directed movement of large masses of seawater. They can be divided into two main types. Surface currents, which occur in the upper few hundred meters, roughly the top 10% of ocean water volume, and are primarily driven by wind. And deep water currents, which involve the other 90% of ocean water, move much more slowly, and are driven mainly by differences in water density caused by temperature and salinity variations, and gravity. This deep circulation is often called the thermohaline circulation.
How fast do they move?
Speeds vary a lot. Surface currents are generally faster, sometimes exceeding 5 knots, about 9 kilometer or 6 mile per hour, in strong currents like the Gulf Stream. Deep currents are much, much slower, often less than 0.5 knots. But because they involve such huge volumes of water, they transport enormous amounts of energy and mass over long distances.
What are the main forces driving surface currents?
Primarily the friction from prevailing winds blowing over the ocean surface, like the trade winds driving equatorial currents westward, and the westerlies driving currents eastward in the mid-latitudes. The Coriolis force is also critical. deflecting the moving water to the right in the northern hemisphere and left in the southern hemisphere, causing currents to flow in large circular patterns called gyres. The shape of the ocean basins and coastlines obviously constrain and direct the currents too. Gravity and pressure gradients within the water also play a role.
And their biggest role is distributing heat around the planet.
That's arguably their most important function for global climate. Just like the atmospheric circulation, ocean currents play a crucial role in transporting heat from the warmer equatorial regions towards the colder polar regions and bringing cold water from high latitudes back towards the equator. This helps moderate global temperature differences and makes the planet more habitable overall.
So we've journeyed from the Earth's fiery core through its shifting plates and sculpted surface to the swirling atmosphere and the vast moving oceans. Now let's turn our focus to the life that thrives within these systems and the challenges it faces today.
Right. Part 4. Life on Earth and the Challenge of Change. This brings us to biodiversity and climate change.
Biodiversity sounds like just variety of life, but it's more complex.
It is. The term combines bio, life, and diversity. Variety. It encompasses the number and variety of all living organisms in a given region. Plants, animals, microorganisms. But it operates on multiple levels. There's species diversity, the number of different species and their relative abundance. Genetic diversity, the variety of genes within a single species. And ecosystem diversity, the variety of different habitats, biological communities, and ecological processes. It's the sum total of life's variety, resulting from billions of years of evolution.
And this diversity isn't spread evenly across the planet, is it?
Not at all. The sources clearly state that biodiversity is consistently richer in the tropics, especially in environments like tropical rainforests and coral reefs. As you move towards the polar regions, the number of different species generally decreases, although the population sizes of those fewer species might be very large.
Why is biodiversity considered so important? What's the big deal if we lose some species?
Multiple reasons are given. There's the ecological role. Every species plays a part, however small it might seem, in the functioning of its ecosystem. Ecosystems provide essential services that humans depend on, like clean air and water, pollination, soil formation, climate regulation. We are part of these ecosystems.
Economic reasons, too.
Yes, there's the economic role. Biodiversity provides us with resources, food, fiber, timber, medicines, genes for crop improvement. Many industries rely directly or indirectly on biological resources. And there's the scientific role. Studying biodiversity helps us understand how life evolved, how ecosystems function, and the specific roles different species play. It's a library of life's solutions.
The sources also emphasize an ethical dimension.
Yes, this is important. The idea that each species has an intrinsic right to exist, regardless of its direct usefulness to humans. From this perspective, deliberately causing extinction is morally wrong. The level of biodiversity is seen by some as an indicator of the health of our relationship with the rest of the living world, and respect for biodiversity is integrated into many human cultures.
But sadly, the sources make it clear that we are currently experiencing a significant loss of biodiversity.
Yes, this is happening at an alarmingly accelerated rate, and it's largely driven by human activities. The primary drivers mentioned are linked to human population growth and increasing resource consumption.
Like habitat destruction.
Habitat destruction and fragmentation is probably the biggest single cause. Deforestation, especially in tropical rainforests, which hold maybe 50% of the world's species, is particularly disastrous. Converting natural habitats to agriculture, urban areas, or infrastructure wipes out the species that live there.
What else contributes to this loss?
Overexploitation, harvesting species faster than they can reproduce. Overfishing, overhunting, illegal wildlife trade. Natural calamities like earthquakes, floods, volcanic eruptions, fires, and droughts can also damage habitats and reduce populations, but human pressures often make ecosystems less resilient to these events.
Pollution. Introduced species.
Yes, pollution is a major factor. Pesticides, industrial chemicals, heavy metals, plastic waste can directly poison organisms or degrade their habitats, particularly affecting sensitive species. And the introduction of exotic species, non-native species, into new environments where they lack natural predators or competitors can cause huge damage. They can outcompete native species for resources, introduce diseases, or become aggressive predators, leading to declines and extinctions in native communities. Think rabbits in Australia or zebra mussels in North American lakes.
And direct hunting and poaching for specific high-value species.
Right. Things like tigers for their skins and bones, elephants for ivory, rhinos for their horns. This illegal trade continues to push many iconic species towards the brink of extinction.
Recognizing this crisis, conservation efforts are underway. What do they involve?
The goals are multifaceted, primarily to preserve endangered species and prevent further extinctions through targeted management and protection plans. This often involves protecting not just the species, but also their critical habitats.
Like protecting areas for breeding or feeding.
Exactly. Safeguarding habitats needed for feeding, breeding, resting, nursing young is crucial. Conservation also involves preserving the genetic diversity within species, including varieties of food crops, timber trees, livestock, and importantly, their wild relatives, which might hold genes useful for future breeding programs. Identifying and protecting the habitats of these wild relatives is key, and regulating or banning international trade in endangered wild plants and animals is another vital tool.
The sources mention India's Wildlife Protection Act of 1972 as an example of national action.
Yes, establishing legal frameworks like national parks, wildlife sanctuaries, and biosphere reserves to provide protected areas for wildlife is a fundamental conservation strategy employed by many countries. These are vital efforts, though the scale of the challenge is immense.
And this brings us to the other massive challenge the sources discuss, climate change.
A huge topic, intertwined with biodiversity loss.
The first point the sources make is crucial. Climate is not naturally static. It's always been changing.
Absolutely. That's very clear from the geological record. Earth has cycled through major glacial periods, ice ages, and warmer interglacial periods numerous times over the past few million years. Looking at shorter timescales, things like tree rings can show past variations in rainfall, wet and dry periods. Historical records document famines, migrations, and societal impacts related to climate shifts and vagaries.
The Rajasthan desert example is interesting.
Yeah, showing it was wetter and cooler around 8000 BC, supported the agricultural Harappan civilization between about 3000 and 1700 BC, with higher rainfall than today, and then became much drier. That's natural change over millennia.
So we know about past ice ages.
Right. The sources mention Earth being generally warm 500-300 million years ago. The Pleistocene epoch, the last couple of million years, was characterized by repeated glacial-interglacial cycles. The last peak glacial period was around 18,000 years ago, and we are currently in an interglacial warm period that began about 10,000 years ago.
And even in recent history, there's been variability.
Yes, the 1990s were noted as being particularly warm with extreme events. The Sahel drought in Africa in 1967-77 and the U.S. Dust Bowl in the 1930s are examples of severe regional climate events. Historical records show impacts like crop failures leading to migration. Europe experienced the Little Ice Age roughly between 1550 and 1850. Looking at instrumental records, there was an upward temperature trend from about 1885 to 1940, then a slight slowing or cooling, followed by renewed warming after the mid-1970s.
So if change is natural, what's the specific concern now?
The concern is about the rate and the cause of the warming observed, particularly over the last century or so. While natural factors, like variations in Earth's orbit, the astronomical causes or volcanic eruptions, terrestrial causes, definitely influence climate, the sources focus heavily on the role of human activities increasing the concentration of greenhouse gases, GHGs, in the atmosphere.
This leads to the concept of global warming via the enhanced greenhouse effect.
Exactly. The atmosphere naturally contains gases like water vapor, carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O, that act like the glass roof of a greenhouse. They let sunlight, shortwave radiation, pass through to warm the Earth's surface, but they absorb a significant portion of the heat, long-wave radiation, emitted back by the warm surface, trapping some of that heat and warming the lower atmosphere. This natural greenhouse effect is essential. Without it, Earth would be freezing.
But the problem is we're adding more GHGs.
That's the issue. Burning fossil fuels, coal, oil, natural gas, deforestation, certain agricultural practices, and industrial processes release large amounts of extra CO2, methane, and other GHGs into the atmosphere. This enhances the natural greenhouse effect, trapping more heat and causing the average global temperature to rise. That's global warming.
And the temperature records show this happening.
Yes, the sources cite the instrumental record showing an increasing trend in global average near-surface air temperature during the 20th century, with an overall rise estimated at about 0.6 degrees C. They note that the warming occurred in distinct phases, particularly from 1901-1944 and again from 1977-1999, with each period showing about 0.4 degrees C warming. And critically, the warmest years in the record from 1856 up to 2000 were concentrated in the last decade of that period, with 1998 being the warmest single year of the century and possibly the millennium.
So The main worry is about the potential consequences of this human-caused acceleration of warming.
Yes. Because the climate system has inertia, the warming caused by past and present emissions is difficult to reverse quickly. While the specific effects will vary from place to place, the overall expectation is for potentially adverse impacts on natural ecosystems and human societies, the life support systems.
Sea level rise is a major concern, you mentioned.
A huge one. As the oceans warm, the water itself expands, thermal expansion. Additionally, glaciers and ice caps on land are melting at an accelerated rate, adding more water to the oceans. This combined effect leads to global sea level rise, which poses a serious threat to low-lying coastal areas and island nations through increased flooding, erosion, and saltwater intrusion into freshwater supplies. This could lead to significant displacement of people and major social and economic problems.
Have there been international efforts to address this?
Yes. The sources mention the Kyoto Protocol as a significant early international agreement. Adopted in 1997 and entering into force in 2005, it legally bound 35 industrialized countries and the European community to reduce their collective emissions of 6 major greenhouse gases by an average of 5% below their 1990 levels during the first commitment period, 2008-2012. It represented a first step, though subsequent negotiations have continued to grapple with this complex global challenge.
And the section ends on a note of hope, or perhaps a call to action.
Yes, expressing hope that the global community will respond effectively and transition towards a more sustainable and livable lifestyle, considering the well-being of future generations. It connects the scientific understanding directly back to our collective choices and responsibilities.
Which brings us pretty much to the end of our deep dive through this incredible stack of sources. We've literally journeyed from the Big Bang and the formation of Earth,
through the workings of its deep interior, the dance of tectonic plates,
the relentless sculpting of its surface by water, ice, and wind,
the complex dynamics of its atmosphere and oceans,
and finally, to the amazing tapestry of life it supports, alongside the profound challenges of biodiversity loss and climate change.
It's been a really comprehensive exploration of the core concepts in physical geography. We've touched on how the planet formed, its internal structure, the continuous work of those geomorphic agents, the global circulation of air and water, the value of biodiversity, and the reality of ongoing climate change.
And what really stands out for me, running as a thread through absolutely everything we've discussed, is how incredibly interconnected it all is. Nothing happens in isolation.
Absolutely. The atmosphere drives ocean currents, which in turn influence regional climates. Weathering provides the raw material that rivers and glaciers then transport to shape landscapes. Plate tectonics builds mountains and ocean basins, but also triggers earthquakes and volcanic eruptions that reshape the surface. Climate patterns profoundly affect which geomorphic processes are dominant and where different forms of life can thrive.
And now, human-induced climate change is acting as this huge overlay, influencing and altering nearly all of these natural systems and their interactions simultaneously.
Understanding these fundamental processes, these connections, gives you, our listener, a much deeper appreciation for the planet you live on. It helps make sense of the natural events you see or hear about in the news, why earthquakes happen where they do, how powerful storms form, why coastlines change, why deserts look the way they do.
And it provides really essential context for understanding the major environmental challenges we face collectively today, like climate change and the biodiversity crisis.
It truly is about being an informed inhabitant of planet Earth. Equipping yourself with this kind of knowledge helps you understand the dynamics that literally shape your world every single day.
So when you boil it all down, what's the big takeaway message?
I think it's twofold. First, that Earth is an incredibly dynamic, complex, and constantly changing planet, driven by immense natural forces operating over vast timescales. But second, and increasingly importantly, that human activity is now a geological force in its own right, significantly altering planetary systems, particularly the climate and the biosphere, at an unprecedented rate.
Which leaves us with a final, perhaps challenging thought for you to consider. We know climate has always changed naturally throughout Earth's long history. But given the evidence that we are now the primary driver accelerating this change, how does that fact fundamentally alter our relationship with the planet? What kind of responsibility does that place on us for its future state?
Yeah, that's something significant to reflect on as you continue to observe and learn about this incredible, dynamic world we live on.
A lot to think about indeed. Thanks for joining us for this deep dive.